The last topic we're going to discuss is how to build a binary heap if you are given a set of numbers. There are two approaches which are called top-down and bottom-up. The top-down is nothing new actually, it's just repeated insert. We have already seen the enqueue method, so just repeatedly call it to enqueue your elements, and that will give you the top-down. Okay, so simply repeated enqueue. And we saw how to do the enqueue. After inserting a key, if the heap property is violated, it has to be restored, calculating upward. Okay, this is the algorithm. Just for I from 0 to the number of elements that you have, just read the next key and then enqueue it. So just repeated enqueue. This is called top-down. There's nothing new about top-down method. Let's take an example. Suppose you are asked to construct a heap using these numbers, using the top-down method. Now here you have to be told what type of heap. Is it max heap or min heap? Okay, so here it says build a max heap using the top-down method with the following keys. So let's do it step by step. First we insert 4, or we enqueue 4. Obviously 4 is the only element, so there is nothing to calculate up. Okay, next we enqueue 6. This is the only place we can add a new element. Okay, but now after that we have to check. Given that we are creating a max heap, if 6 is bigger than its children, it has to keep going up until we find the right place for it. So in this case, 6 is indeed greater than 4, so we have to calculate up, and this is what we will end up with. Okay, so that is the end of inserting 6. Now insert 10. 10 will go to the right of 6. Okay, but again it is violating the max heap property, so we have to calculate it up, swapping with 6, which will give you this. So 10 will go up, 6 will come down. Okay, next we enqueue 20. 20 can only go to the right of to the left of 4. Again, the 20 has to be calculated up until it reaches the root, because it's bigger than both 4 and 10. Okay, if you are doing this in an exam, probably you don't have to show the immediate step here. You can show directly where 20 will end up with. Where 20 will end up. It will end up here after 2 calculate ups. Okay, finally we enqueue 8. 8 can only go to the right of 10. Okay, unlucky for us, this time 8 is in the right place because it is less than its parent 10. So there is no calculate up to do after inserting 8. So this is building a heap top down. It's really nothing new. It's just repeated enqueue. Okay. It's another example from the book. Also creating max heap. So there is nothing different actually from the first example, other than that they are also showing you the content of the array. Remember the tree, even though conceptually it is a tree, it is really an array. So it is showing you how the element grows in the array itself as well as you are doing the enqueue. So enqueue 2, it is the only element, nothing to do. Enqueue 8, it has to calculate up. Enqueue 6, it will go to the right, nothing to do, it is in the correct place. Enqueue 1, again nothing to do, it's in the correct place. Enqueue 10, this time it has to calculate twice, here and then here, as you can see. So this is after enqueuing 10, this is what you have. Next we enqueue 15. It has to go all the way top. So first it come here, then it come here. 3 will be in the right place, nothing to do. And 12, however, will percolate until here. Okay, so that's what you have here. 12 first here, then here. Finally 11, you only need to percolate it one time and it will reach here. So this is building a heap top down. However, there is a second method to build a heap, which in fact is more efficient than building a heap top down. So this involves converting a data that is already in an array into a heap. In other words, to build a heap using the bottom-up approach, or Floyd method as it is called, we will see the name in a moment, we don't insert the elements one by one. No, we just store them all at once in an array, then convert that array into a heap following a process. So that process is what we're going to explain. So that's the difference between bottom up and top up. Top down and bottom up. Yeah, it said this method was introduced by a guy called Robert Floyd. So it's called Floyd method actually. And it is generally more efficient than top-down approach. I will explain why after we have seen how it works. This is the algorithm. So assuming you have already put all the elements in an array, then you're going to start a loop. But this loop is going to work from the bottom up. This is why the method actually is also called bottom up. It's going to start with I equal to index of the last non-leaf. So this is actually, again, the reason why we needed the other formula. How do we know the index of the last parent? Okay, so we go from that number down until 0. Okay, or rather up until 0. Okay, if we're thinking of it as a tree, of course the values are decreasing, so we can think of them as down from 10 down to 0. But looking at it from the index of a tree, and given that the root is at 0, we're actually going up the tree. So that's why it's called bottom up. Okay, so for each value of I, restore the heap property for the tree rooted at I by simply calling percolate down method. So I just remind you the index of the last non-leaf node, you obtain it using this formula, n over 2 minus 1. We shall see actually in terms of implementation, this algorithm can be implemented simply by repeatedly calling percolate down at I, where I start from last parent until 0. So for I from last parent, as long as I is greater or equal to 0, percolate down at I, then decrement I by 1. So eventually I will be negative and we will stop. Okay, so we shall see, let's see actually how do we do this using example. So he said here, convert the following array to a min heap using the bottom up approach. So we already have our elements. The first thing we do is we put all of them in a tree in breadth first order. So 70, 29, 68, exactly as they are here. 65, 32, 19, 16. But of course, you must be constructing a complete tree, otherwise it's not going to be a heap. So top to bottom, left to right. So this is step number 1. Put all the elements in a binary heap or in a complete tree. Next, we identify the index of the last parent. As you can see here, the last parent is 32 because the next element is a leaf, it's not a parent. Okay, so index of the last non-leaf is 0, 1, 2, 3, 4. Okay, index of 32 is 4. So we're going to vary our I from 4 until 0. Yeah, I'm calculating here, showing you how to calculate the last leaf, last non-leaf it should be, last parent, sorry. So it's n over 2 minus 1, which in this case is 10 over 2 minus 1. Well, 10 over 2 is 5. 5 minus 1 is 4. So the last parent, not last leaf, last parent is 4. Or last non-leaf, either way you want to call it. So it means we're going to vary our I from 4, 3, 2, 1, 0. Okay, going up the tree. This is number 4, then number 3, then number 2, then number 1, then number 0. So we are going up the tree. This is why it is called bottom up. Okay, so for each I, we take note of the tree rooted at I and try to calculate the parent of that node down if necessary to restore the ordering property, because we just entered the element randomly without regard to the ordering, so they may not be satisfying the binary heap ordering property. In this case, for min heap, we are asked to construct a min heap. All right, so if you see 32 is bigger than 31, so definitely there is a need for swap here. Since we are constructing a min heap, 31 will go up and 32 will come down. So it says here, at each stage we need to convert the highlighted tree. We will be highlighting the tree in red, the tree rooted at these indexes. So first the one at index 4, okay, convert it into a heap using calculate down, starting with its root. So the root of this tree is 32, and this is our reference point. We need to calculate it down. Okay, so 32 will go down and 31 will go up. 32 will now be a leaf, so we are done with that particular step. Okay, so as you can see, 32 has come down, 31 has gone up. Then next you consider index 3. Okay, this is index 3. Okay, 0, 1, 2, 3. So consider the whole tree rooted at 3. This is the tree rooted at 3. And again, your reference point is the root of that tree. Calculate it down. So in min heap, we swap the parent with the smaller of the two children. In this case, 13 is smaller. So 13 will go up, 65 will come down, and we are done with this small tree. As you can see here, 13 has gone up, 65 has come down. Next, we take index 2, which is here. Notice a common mistake is for students, after they finish this, they go to 29. No, it's not how to do it. You have to follow the index correctly. 4, 3, 2, 1, 0. Okay, if this is 3, this is not 2, this is 2. This is 1. So after 3, you have to go to 2. Okay, so the next tree to concentrate on is the one rooted at 2. Okay, so again, the reference point is the root. Try to calculate it down, swap it with the smaller child. The smaller child is 16. So 16 will go up, 65 will come down. Okay, as you can see here, 16 has gone up, 68 has come down. Then now you can go to index 1, which is this tree. Okay, I is equal to 1. Again, Our concern is just the root. Calculate it down. Don't worry about any other element. Just calculate the 29 down. So 29 against its two children. It is smaller than 31, so we cannot go to the right, but actually it is smaller than the left child, so it has to come down. So 13 will go up. But you don't stop there. Again, you compare 29 with the two children. Okay, it is 26 is smaller. So 26 will go up and 29 will end up here actually. So this is what you will end up with. You can see 29, which was the root of that tree, has ended up here. 26 has moved up and 13 has also moved up. Okay, so this is the result of calculating the 29 down. Finally, we go to index 0, which is the entire tree itself. I equal to 0 means you have to look at the whole tree, but concentrating only on 70. Calculate the 70 down. So 70 against 13 and 16. 13 is smaller, so it will swap with 13. 13 will go up, 70 will come here. And then you repeat. 70 against 26 and 31. 26 is smaller, so 26 will go up and 70 will be here. Okay, again 70 against 65 and 29, it is still bigger than both, and 29 is the smaller one. So 29 will go up and 70 will come down and 29 will go up. So eventually this is what you will have. See, 70 has been calculated down all the way along this path. Okay, so this is where 2070 will end up with. And if you look at the tree now, even though we entered the numbers initially randomly, now it is actually a mean heap. See, 13 is smaller than both its two children. 26 is smaller than both its two children, and so on. So this is how to construct a heap using the bottom-up approach. Now, I asked a question earlier saying, why do you think this Floyd method is more efficient than the top-down method? Here is the answer. You see, in the bottom-up method, or in the Floyd method, you're going to start from the index of the last non-leaf. Okay, so for example, here when we have 10 elements, I believe they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We started from 4 and go up until 0. Essentially, we have to do at most half the number of elements, number of calculate ups. We have to do calculate up 1, 2, 3, 4, 5 times. So n over 2 calculate ups are needed. Now consider the other way around using the top-down method. How many calculate ups do you have to do in the worst case, in the worst scenario? If you are inserting 10 elements, the only one you are guaranteed will not involve calculate up is the first one, because it's the only one. So if you have 1,000 elements, it is possible that you have to do 999 calculate ups in the top-down method. In the top-down method. Whereas here, you only have to do n over 2 calculate downs. So instead of 1,000 or instead of 999, now you only have to do 500 n over 2. So you can imagine the difference. Okay, you can basically do half work using the bottom-up approach compared to top-down approach. Here we don't have to do n time, we have to only start from the index of the last parent, which is normally halfway through the tree. Just do n over 2 or minus 1, you will get that index, and now you need to do a loop from that until 0, not from 0 to n as in the case of top down. So this is why the bottom-up approach is usually more efficient. This is another example from the book showing you how to do the same thing. I think I don't need to explain anything, it's the same thing. Just count the number of elements we have: 1, 2, 3, 4, 5, 6, 7, 8, 9 this time. So 9 over 2 will be 4, minus 1 will be 3. So you only need to start from 3 until 0. This is index 0, 1, 2, 3. So start from index 3, make sure this is a heap, then go to index 2, make sure it is a heap, then go to index 1, make sure it is a heap, and then go to index 0, make sure it is a heap, and that is it. Okay, exactly as we saw there. Of course, this one is with min heap. So this is basically the idea of building a heap top down and bottom up. And actually this brings us to the end of this lecture and the end of our discussion on binary trees. Thank you very much.